Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course elements of mechanical vibrations. Last time we started with a typical 2 degree of freedom system and derived governing equations, discussed what principal motion concept and derived the expressions for the natural frequency. In today's lecture we continue our discussion and in particular we will be focusing on the concept of mode shape. Okay, so we discussed as to how for this 2 degree of freedom system the governing equations of motion are obtained. So, these two were the two coupled governing equations of motion, and then we discussed that there is a special solution possible for this 2 degree of freedom system, wherein both the masses move harmonically at the same frequency of oscillation. Okay. So, we imposed or assumed the general solution of the two coupled governing equation of motion that they are given by capital X1 cos Pt and X2 as capital X2 cos Pt. So, now both the masses that is 1 and 2, they are moving with the same frequency of oscillation, which we denote for a change here instead of omega n I am using p just to avoid subscripts and then make it a little more convenient for writing purpose. Otherwise this p represents basically natural frequency. Now, the two masses could move with different amplitude values. So, x1 and x2 are the two amplitudes of motion for mass m1 and mass m2, okay. But their frequency of oscillation is assumed same, okay, and it is possible that such motion exists for both the two masses, wherein the two move with the same frequency. And we discussed in our previous discussion that assume that K2 is assume the motion that K2 is not stretching or compressing. So, in that case you can assume that mass m1 is moving as a single degree of freedom system which is defined by this system, and the mass m2 moves as a single degree of freedom system defined by the frequency which is given in terms of m2 and K3. Basically it is possible that for certain conditions the two masses move harmonically with the same frequency. So, we tried to check whether this is really possible or not, and the way to do is assume such a solution and then substitute in the governing equation and look for the expression for such a frequency p, and then we when we substitute that, these are the two equations that turns out which we derived, and then it tells by rearranging this we get two amplitude ratio x2 by x1 given by this expression on the right hand side, x2 by x1 from the second equation given by the expression on the right hand side like this. And then by equating these two amplitude ratios we obtain the characteristic equation or a polynomial in p square that gives you the natural frequencies, the two natural frequencies. So, it indeed is possible that if certain conditions are met, the two masses will move with a frequency given by this expression. So, solving this quadratic equation we get basically the two possible frequencies P1 and P2, P1 given when we use negative sign of the two possible signs here, and then we will get the other one P2 by assuming a positive sign. So, the lower one we typically call as P1 and the higher one we typically call as P2, the higher of the two natural frequencies. Okay. So, so what will be these two natural frequency? These two natural frequencies, that one will be when the system will move with a frequency of P1 and the other one will be when the entire system moves with the frequency P2. I am going to explain that to you very shortly in more detail, but what you should understand that you will get one value for P1, I mean one value for P, that is P1, the other one will be P2. These are the two natural frequencies of the system. Now, we already know that if we have 2 degrees of freedom, there will be 2 natural frequencies, and therefore, in this solution we will get 2 natural frequencies. What is important again is that we have assumed x1 t to be equal to capital X1 cos Pt. Now, in this case that P will become, let us say, P1. Okay. Similarly, mass M2 is going to oscillate given by the solution cos P1 t. Okay. So, mass M1 and mass M2, both of them will oscillate with the same natural frequency P1, okay, and then they will have amplitudes x1 and x2. Now, these are the relations, this one and this one, but both of them basically gives you the same amplitude ratio. This expression actually tells you what would be the ratio of amplitude x1, or we can say amplitude ratio x2 and x1, meaning thereby that the expression here will tell you what should be the relative amplitudes of mass M2 here and relation to the amplitude of mass M1 should be, so that the entire system that comprises mass M1 and M2 will oscillate with the frequency P1. And how do you get this x2 over x1? By substituting for this P square as P1 square. Okay. When you substitute in this expression, let us say if I call this as expression 1, by substituting P equal to P1, you will get some number or some numeric value. That numeric value is going to tell you what is the amplitude ratio between mass M2 and M1, which is maintained when both of them oscillate with the frequency P1. When you substitute for P equal to P2, then you will get a different amplitude ratio. Okay. When you substitute P equal to P2 in the expression 1, you get some other number, and that number will give you the ratio of the motion of the two masses, and that will be clear very shortly. And basically the emphasis is on telling you that what is the relevance or what is the significance of this amplitude ratio that we have obtained. Okay. Now, we shall have a detailed look on what is known as a mode shape. Now, what are those mode shapes is something which we will try to understand. Now, I am reproducing this particular 2 degree of freedom or a 2 mass system as an example, and for the sake of some mathematical simplification without losing any generality in that sense, we essentially make small assumption that the values of the stiffnesses K1 and K3 are equal, and it is equal to K, and the stiffness K2 is 2K. Okay. So, this K1 is assumed equal to K, and this is assumed equal to 2K, and this is assumed equal to K, just for the sake of mathematical simplicity in the evaluation process. And so, M1 and M2 are equal to M. If we now use these values in the expression general frequency equation that we have obtained, it is quite simple and straightforward to solve this equation, and then you will find that solution gives the first of the two natural frequencies is going to be square root of k over m. The second one however will have this value square root of 5 k over m. You can try it out yourself, but these are the two natural frequencies. You can directly substitute, instead of solving this quadratic equation, you can actually substitute these values into the frequency equation or a direct solution of the frequencies. Using this equation also you can get the two expressions P1 and P2, but you will definitely get the same answer here. All right. Now, you can also have a look at particularly this particular frequency, the first of the two natural frequency. Now, it says that your natural frequency is square root of k over m. Okay. It actually means then that if this stiffness is k and this is m and this is m and this is k, it will so happen that the motion of the two masses x1 and x2 will be such that they will be having the same amplitude and k2 will not really stretch or compress. Okay. That is something which we will soon going to find out, but this simple expression of square root of k over m, it actually indicates that at first natural frequency this system will be almost independent of the second system. Okay. We will figure that out very shortly, but in addition to the natural frequency, we have the expression of x2 over x1 which we have derived in the earlier slide, and that is given in terms of k1, k2 and m1. Now, this expression, if you substitute for these two these assumed values of k1, k2, k3 and m1, m2, you will find that by substituting for k1 equal to k and k2 equal to by substituting k1 equal to k and k2 equal to 2k, and also we have to substitute p either as p1 or p2 depending upon what amplitude ratio you want for which particular natural frequency. So, what I am doing here is I am substituting for p square as p1 square, which is going to be k over m, and you can see that by when I substitute that, this entire expression evaluates to 1. You can just cross check it yourself. So, x2 over x1, this amplitude ratio x2 over x1 is turning out to be 1 for the case p equal to p1, which actually means that when the system vibrates at its first natural frequency p1, x2 is equal to x1, x2 by x1 equal to 1, which actually means that x2 is equal to 1, okay, which means that the amplitudes of this mass when it vibrates at p1 natural frequency and the amplitude of x2 when it vibrates at the same natural frequency, this amplitude x2 is same as this amplitude x1. That is what it is, this is x1, this is what it is actually meaning. Okay. And if I want to now show this shape, okay, in the form of a figure here, I will show it this way, that instead of showing the motion in the vertical direction, which is basically the degree of freedom, it becomes easier for me to represent that motion or that amplitude in the lateral direction, or in horizontally I will show that motion. So, this is the position of mass m1. At the same time, mass m2 will also move in the same direction. Now, the direction actually, if this direction is downward positive, then this also is going to be downward positive with the same amplitude, which I am showing just for the sake of illustration in this figure. in the horizontal sense. This spring is fixed here and the spring gets stretched as it moves, and the same way this spring is also stretched in the same direction. Okay. So, the motion x2 and x1 are identical. So, this is +1 and this is also +1, and that gives me relative displacement of the two masses m1 and m2 when the masses are moving at its fundamental or first natural frequency p1. So, this is the mode shape, okay, corresponding to the first natural frequency. Okay. Mode shape is always defined in the context of a particular natural mode of vibration. Okay. So, this x2 by x1 equal to 1 represents the mode shape at the first natural frequency, and therefore, it is also called the first mode shape. Is that clear to you? So, this is how the two masses will move, and that movement is captured through this shape, and at any instant of time the two masses will have the same displacement ratio. That means, if this is 1 unit, this is 1 unit. If this is displaced let us say 2 centimeter, this mass will also be displaced 2 centimeter in the same direction. Okay. And because it is defined as a ratio, the absolute amplitude makes little relevance. I mean, it is not how much, whether it is 2 centimeter or 2 millimeter does not make any difference, as long as the ratio between their displacements is maintained equal to 1, that is what the mode shape is. Okay. I will show you more details of this mode shape very shortly, but let us now look at what happens when I substitute for P equal to P2. That means, in this expression if I substitute P equal to P2, then what happens? So, if I substitute P as P2, we know that it is square root of 5k by m. So, this expression now P squared gets replaced by 5k over m, and you can show that it turns out that this entire numeric value is equal to -1. This expression, the ratio, turns out to be -1, and I shall be referring to these mode shape ratios as, or these amplitude ratios as XR1 to represent that as that it is the ratio of the amplitudes in the first mode shape, and the amplitude ratio XR in the second mode shape. So, this is in the first mode shape I am basically having XR1 equal to 1, and that is positive, whereas XR2, which is the amplitude ratio in the second mode or in the second natural frequency, equal to -1. That is what we have obtained here, the ratio of the two amplitudes as -1. Now, how do I represent -1 and what it actually means to me? Which actually means that when the amplitude of mass m1 is 1 unit in its positive direction, then at the same time the amplitude of mass m2 will reach the same amplitude, but in opposite direction, because the direction is now negative. So, how do I represent that? I represent it this way. So, what I say is that this mass, when it moves in the positive direction by 1 unit, okay, when x1 is equal to 1, x2 is equal to -1. So, it goes in the opposite direction. Okay. So, what is going to happen when the entire system vibrates at its second natural frequency? Then in that case, when mass m1 is moving this way in the first half cycle, mass m2 is going to move in the opposite direction. mind you x1 and x2 are defined positive downwards. So, in the first half cycle of oscillation, if mass m1 goes down like this, the mass m2 goes up like that, and then it will complete its cycle like this, and whereas here it will complete its cycle here. It should be noted and noticed that the amplitude will remain the same, this x2 sorry this x1 and x2, both of them will have same amplitude because the ratio is 1. The only thing is their senses or their direction of motion will flip at the same instant of time. So, at any instant of time, if x1 or m1 is moving downwards, m2 will move upwards, and when it is m1 is moving upwards, it will move downwards. So, that is how these two will maintain the ratio of -1. So, it is not only please make a note here that it is not only this peak amplitude to be identical. If you take at any instant of time like this, if I take at any instant of time this amplitude for time t is equal to, let us say t1, the amplitude of mass m1 is going to be so much, let us say 0.7 units. At the same time, amplitude of mass m2 will be minus 0.7, okay, and that ratio will remain the same, right. So, 0.7 divided by minus 0.7, that -1 ratio remains the same at each and every instant of time in the whole cycle of oscillation. And needless to say that the moment the time required for mass m1 to finish one oscillation is going to be exactly same for the time required to finish the oscillation for mass m2. So, the time period of both of these two masses will be same, and therefore, we know that it is going to oscillate at the same natural frequency. So, there is nothing like natural frequency of mass m1 and natural frequency of mass m2, it is not like that. It represents the natural frequency of the entire system. Here we have just two masses. You can imagine that there are hundreds of such masses, and all of them will keep on moving naturally freely at the frequency which is the natural frequency of that particular mode. Okay. So, n degrees of freedom, n natural frequencies, and there are corresponding n mode shapes. Each natural frequency has its own mode shape associated with it, okay, and it represents the relative amplitudes or relative displacement of individual masses of that system. Okay. Now, the animation here will give you a very good sense of what we have seen and discussed. So, this is how the first mode shape for this particular system, where k1 equal to k2 equal k1 equal to k3 equal to k and k2 equal to 2k looks like, right. So, of course, the mass here is moving up and down. Here for illustration sake, that vertical motion is represented horizontally, so that the individual masses positions become clear to you, and at the same time their amplitudes are shown as a function of time. Okay. So, on the x axis you have time, and this is the displacement. Okay. Now, let us look at this again and have a look at their relative amplitude. See, both of the masses m1 and m2 are moving with the same amplitude. If I halt it at any instant of time, their displacements are identical. Okay. So, if I move them slowly, so here you can see at this instant of time their amplitude ratio will be 1. If I slightly move it, both of them are negative or in this case positive, so it will remain positive. Here at this instant of time, both of them are moving in the negative direction, their values will be both numerator denominator negative, but equal in magnitude. So, the ratio turns out to be still 1. And look at this, this at this instant of time, if I draw this line, they are reaching their peak values at the same instant of time, and they have to, otherwise they will not do a harmonic motion, they will not execute a harmonic motion. So, this is how a mode shape is going to look like. Interestingly, just have a look at what is happening to this spring. It is not at all stretching or compressing. You see that? What was the stiffness of this spring? K for our simplified system. This is mass m, this is also mass m, this is your stiffness K. This although was 2K, but in this particular mode, because this amplitude and this amplitude are same and in the same direction, makes the spring ineffective, or it is not contributing to the motion or to the vibratory response. And therefore, you can then notice that this system is independent of this system, both of them are independently vibrating, although they are connected through a spring to which is having stiffness 2K, but then essentially and effectively these two spring mass systems are almost independently moving, right. And that is the reason why we found that P1 is equal to square root of K over M. Okay. Are you clear about the mode shape? Now, the mode shape is the relative deflection or a displacement profile or displacement ratios of individual inertia elements of a vibratory system, and it has nothing to do with the actual individual displacement value. For example, the meaning of that is, it does not matter whether this is 1 millimeter or 1 centimeter or for that matter 1 meter. Okay. So, if this is 1 millimeter, this should be 1 millimeter. I mean, the ratio x2 over x1 should be the same. Now, I am writing here 1 does not mean that in all the 2 degree of freedom system the x2 by x1 will be 1. The moment you change these stiffness values and mass values to be arbitrary, the ratios will completely change. Okay. It might be 0.4, it can be 1.1 or whatever. 1.1 normally we normalize it with respect to the displacement of mass m1. Okay. Okay. Now, let us look at the second mode shape. Now, in this case what happens is that the two masses, you can now notice that when this mass is moving down, this mass is going up. Okay. So, their amplitudes are always in opposite sign, and now you can see that the middle spring, this spring is effective and it is contributing. Okay. You can notice that the spring is contributing, and that has a very high stiffness, it is twice the spring stiffness of the first and the last spring, and that is the reason why the moment your second spring comes into action, the strain energy stored in that spring becomes it's going to contribute, right, and the strain energy is what, half kx square, right, which means that it is going to, the strain energy will contribute to the numerator. This spring does not have any mass, that is our assumption. So, the moment your strain energy is increased of the system, your natural frequency is expected to increase. So, the moment 3 springs are now effectively contributing in the vibratory motion, we expect the second natural frequency to be much higher than the first one. Is that clear? And also look at how the phases are. So, if I draw a vertical line from here at this particular time, when this is negative, this mass is positive. So, this is the motion x1 and this one is x2. So, at any instant of time the motions are in opposite phase, we call that. So, therefore, for the second mode x2 over x1 is minus 1. Are you clear about this? What is a mode shape? It is a shape, and therefore, it has individual mass displacement amplitude is less relevant than the relative values of their amplitude. So, you should always keep this in mind, that it is the relative amplitude of individual mass elements relative to one of them. I mean relative to, let us say, first mass or last mass. With relative to that, what is the amplitude or the displacement value, that relative value is what is the mode shape. Okay. Now, this is, so therefore, you can also see that the speed with which this motion is happening is much higher than the speed with which the motion was happening in the first mode, because the frequency was lower. Okay. Anyway, so this motion of individual masses is harmonic motion, and what was our assumption in the derivation of all these frequencies P1, P2, x2 by x1? It was with the assumption that my initial amplitude is x1 and initial amplitude is x2, because these equations are always satisfied at all instant of time. So, if I take t is equal to 0, x1 at time t is equal to 0 is going to be x1, and x2 at time t is equal to 0 is going to be x2, which means that at time t is equal to 0, I must give an amplitude, initial displacement and initial displacement to the mass m2 to be such that they have a value which is related. Now, this x1 and x2 for the first mode shape to occur is x2 over x1 equal to 1. Now, because we are showing you the second mode shape, I will write that x2 upon x1 is equal to minus 1, which means that if x1 is equal to 1 unit, what is x2? Minus 1. Okay. So, therefore, and of course, I am assuming here that the displacement here x1 and x2, they are assumed, I mean I am, for the sake of illustration here, we say that this x1 is positive here. So, obviously, although it is here, it does not, in the actual case it is going to be like this. Anyway, so the point here is this mode shape or this displacement, initial displacement x1, capital X1 and capital X2 should be given in a way that it satisfies the mode shape, and only when I give these kind of initial displacement, then the subsequent vibratory response happens in both masses at its natural frequency. Okay, and both the masses move harmonically, both the masses move with the same frequency, either P1 or P2, depending upon how I initially perturbed them. Okay. My initial perturbation, if it is maintains the same ratio, that x2 equal to x1 equal to 1, it will vibrate, both of them will vibrate at its first natural frequency. If I initially give a value x1 equal to 1 unit, x2 equal to minus 1 unit, then both the masses, so I move the first mass vertically up, the second mass vertically down, and then release them, then the motion is going to happen at its second natural frequency, but both of them will move with the same frequency P2 and they will maintain the amplitude ratio as given by the mode shape, right. So, what it actually turns out that in a multi degree of freedom system, you can make the multi degree of freedom system vibrate at a particular natural frequency, provided you give them the initial excitation or initial disturbance maintaining the amplitude ratio or the mode shape. Okay. in that particular frequency. We shall discuss this little in more detail, but then time is now correct to give you an idea of what happens when the initial displacement, that means at time t is equal to 0, x1 at time t is equal to 0, let us say is 0, and x2 at time t is equal to 0. Now, this we know is actually x1 and this is x2, but what I do is I give 1 unit displacement to the second mass, but 0 unit, that means I do not move the first mass, I keep it as stationary, but disturb the second mass, move it downwards by 1 unit. So, you can see that the second mass has moved downward by 1 unit, whereas the first mass remained here, and that is what you are seeing here, 0 motion for the first mass and some positive 1 unit motion to the second mass. Now, is this satisfying any of the two mode shapes? It is not, right. So, if it is not satisfying at t is equal to 0, there is no way it will satisfy at later time, right, because in the initial part itself you have not maintained the amplitude ratio. Now, if that happens, if you give this kind of a arbitrary motion, arbitrary in the sense that which is not at all maintaining the amplitude ratio, then what kind of a motion is going to take place? Look at this. Do you think this motion is harmonic? Either see at this massless movement, or you see how this particular movement is taking place. Let me rerun it for you. You do not see that a harmonic motion happening, right, and it is all because you have not maintained the initial displacement same as or honoring the mode shape, either of the first mode or of the second mode, okay. And that is why the motion that you get is a mix of the two harmonic motions, okay. And the animation that you observed here is definitely not harmonic, okay. It is just an arbitrary free vibration response where the first mode contributes, the second mode will also contribute, and that is precisely the way the motion is going to take place, okay. And that is very interesting and important for us to understand that if you want to excite a vibratory system into one of its natural frequency, then the initial disturbance to it should conform to the mode shape corresponding to the frequency in which you want it to vibrate, okay. If you want this two mass system to vibrate at its first natural frequency, then you should disturb this by giving 1 unit amplitude in the same positive direction to both of the masses and then release them. If you do that, it will vibrate at its first natural frequency, okay. If you move it in the opposite direction, then it will vibrate at its second natural frequency. If you disturb it arbitrarily, okay, neither maintaining the amplitude ratio of the first mode nor of the second mode, then the ensuing vibration response will look like the way you are seeing it here. Now, there is one interesting class of such 2 degrees of freedom system, and so here what we are assuming that K1 equal to K3 equal to 0. That means there is the two springs at the top and the bottom are actually not there, okay. And when they are not there, you are left with only two masses connected by a spring. Now, if that happens, you still can have this frequency equation the way we derived and the amplitude ratio the way we derived, and then when you substitute into this equation, okay, let's do that. So, if it is like p raised to power 4 minus, now k1 and k3 are 0. So, you will have this one as 2k over m and plus 2k over m and p square plus, so k1 k3, and so you actually have 0 here, okay, because k1 and k3 are 0. So, plus 0 equal to 0. So, then you have p square minus what will that be, 2 k over m, sorry 4 k over m, no, right, equal to 0. So, now by solving this you have one of the two natural frequency, so p1 equal to 0 and p2 equal to square root of 4 k over m. So, the second one is of course this, but what is the first natural frequency? 0. Now, what do you make out of the first natural frequency being 0? Yeah. Now, just to give you an example, a practical example, you can imagine a metro coaches, two metro coaches connected by a coupler, right. This is maybe the drive coach and the one is just a trailing coach. You can also connect more coaches, but then just for the sake of discussion here, you can imagine that these are the two masses connected by a coupler which is a spring. Now, what is P1? Can I say right, 2 pi by capital T will be its natural frequency, will be its frequency. Basically, T is the time period of what? Repetition, oscillation. Now, if these two masses simply move together without the spring being stretched, okay, when will it repeat? Suppose in one case of course is that this mass is moving down and this mass is moving up, the spring is completely in action, then the spring will bring both the masses back to its original equilibrium position if they are moving opposite, right. So, the two masses are going to move out of phase and then come back again and then gets compressed and then it will again push it back, right. That kind of a motion is going to happen as one of the two possible motions, but the first motion, okay, when they are moving in the same direction, these two bogies will simply move together, they will move together without getting returned back, without getting returned to its original position, they will not come back, okay. What is the period in such cases? Infinite, which means that what? First natural frequency is 0. It actually means a rigid body motion, okay. P1 being 0 is actually representing a rigid body motion or a rigid body mode, where all the masses move together with the same amplitude in the same direction, okay. Such systems where the first natural frequency is 0 are called degenerate system. So, in this 2 degree of freedom system, the first natural frequency, because the system is unconstrained as such and therefore, both the masses can move freely, and when they move freely in the same direction, there is no restraining force to pull it back, and then the fundamental natural frequency is 0 and the movement is called as a rigid body motion. So, the first one definitely is 0 and the second one of course will have a natural frequency of 4k over m. Okay. And then what happens, of course, as I said, when first mass goes up, the second mass goes down at the same time, and then they will have still a harmonic motion, and the time period of that harmonic motion will be given by 2 pi over capital P P2. Okay. So, the period is going to be identical for both the masses. The only thing is that the spring has to be active, and that happens when both of them move in the opposite direction. You can of course find out by substituting for P2 P by P2 this amplitude ratio, that you can of course find this out. Yeah. So, if this is to be minus m P2 square is going to be 4k over m, and then plus 2k, k1 being 0, and then this is 2k, and so now you can figure that out, like this is going to be minus 2k over 2k, that turns out to be minus 1. So, the mode shape for the second frequency is going to be minus 1, which is expected in this case, right. This is basically your degenerate system. Now, we will formally introduce and discuss what happens when such a 2 degree of freedom system is subjected to initial conditions which do not conform to the any of the mode shapes, okay, or any of the displacement pattern which is expected at t is equal to 0. So, x1 is going to move in a motion which is going to be contributed by both the natural frequency. We expect that because we have seen in the animation also that when you do not maintain the amplitude ratio at t is equal to 0, either conforming to the first mode or a first natural frequency, or conforming to the mode shape of the second natural frequency, then the first mass will not only move with a frequency at p1, but also will be with the frequency of p2, and therefore we can write the general solution to be contribution from the first mode and first natural frequency, as well as from the second natural frequency. Okay. So, the first term in general represents some amplitude value, we do not know how much, first natural frequency which we know, which we can find out from the parameters of the vibratory system, and we have now introduced some phase, okay, phi 1. Similarly, contribution will come from the second mode. So, P2 appears, and the amplitude for the second harmonic as B1 appears here. We do not know how much will be B1, and then of course, as a general response we also add the phase phi 2 to the second part of the solution. So, x1 gets contribution from the first mode as well as from the second mode. Okay. The way x1 vibrates and responds by a joint contribution from the first and second, we can expect the same thing happening with the second mass. The second mass also will move in a similar way, but now the amplitude of the contribution from the first mass may not be the same as for the mass m1. Why should it be identical? It can be different as well, right. And the same thing happens here as well, and these two harmonic terms will remain as they are for the first and second masses. So, the entire solution of the system as a whole will have contributions from all the possible modes of the vibratory system, and therefore, this is a generic solution or a general vibration response to arbitrary initial conditions. Okay. Now, we want this solution to be obtained, and therefore, it should have unknown or computed values of A1, B1, phi 1 and phi 2, and also A2 and B2. Now, you may notice that x2 and also it is implicit that the x1 and x2 are time functions. I mean time, it is a function of time. So, x2 I can write, because at all times if the contribution is coming from the first mode, we all know that x2 upon x1, if the motion is happening in the first mode, honors a particular amplitude ratio. So, xr1, that is what we wrote, right. You remember that in the previous slide we wrote this amplitude ratio as xr1. So, this was written as xr1, meaning that the amplitude ratio xr in the first mode. Okay. So, therefore, I can write A2 as A1, because if A1 becomes the amplitude of the first mass vibrating in the first mode, then I can write this A2 as A1 xr1 cos P1 t minus phi 1 plus and on the same lines x2 over x1 vibrating in the second mode or at second natural frequency is xr2. xr2 represents the ratio, okay, amplitude ratio. So, I can write B2 as B1 times xr2 cos P2 t minus phi 2. Okay. So, in fact, in a more formal way, I can write this in a matrix form as equal to A1 or xr1 or xr1, I may like to use B1 we can write it this way, or you can simply use these two equations to find out x1 and x2. Now, what are the unknowns here now? The unknown are A1, B1, phi 1 and phi 2, because P1 and P2 are known, because you know the system parameters or the vibration or vibratory system parameters like K, M and all. So, P1, P2 is known. In fact, XR1, XR2 are also you must be knowing that these are functions of your K, M, the system properties or the mass and stiffness properties. Similarly, XR1. So, actually XR1, XR2 are nothing but dependent on the system parameters. So, they are actually known through eigenvalue analysis. So, the way we find out P1 and P2, you can also find out XR1 and XR2. So, they are known, only unknowns are A1, A1, B1, phi 1 and phi 2. Okay. Where will you get these two and how many unknowns? 4 unknowns, right. How do I find these 4 unknowns? You remember now single degree of freedom system. Now, in single degree of freedom system you had an expression x1 t which was like a cos omega n t minus phi. Okay. That is the only equation you had, you did not have 2 equations, only one equation because there was only one response, that is, or the one degree of freedom 1 x t. So, and then a and phi were the 2 unknowns. How did you get that? You found out the expression for the velocity and the initial condition x at t is equal to 0 and x dot at t is equal to 0. You use them as x naught and v naught in the by using the 2 expressions displacement and velocities, and we will do the same thing here. We will now get the expressions for x1 dot and x2 dot, okay, and then what is the initial displacement and velocity given to the mass m1, what is the initial displacement and velocity given to mass m2. If you prescribe that, you will get the solution. Okay. Then you will have a complete expression x as a function of time x1 and complete response equation x2 as a function of time. Everything on the right hand side will be known, so that at any instant of time you can find out what is the response, or you can generate the response history as a function of time. Okay. That is how the free vibration response is going to be evaluated. So, the summary of this lecture, we discussed what a degenerate system is all about and particularly its frequency character. We also discussed a lot about what is a mode shape, the concept of mode shape for a multi degree of freedom system and how it appears for a 2 degree of freedom system. Then we had an initial discussion on how to find response to initial disturbance for a 2 degree of freedom system, quite on similar lines to what we had discussed for a single degree of freedom system. These are a few recall questions based on what we discussed today.